This is Milton Kiever, editor of Electrical Design News. I want to take just a moment to indicate the purpose behind this record and those to follow. The major method of communicating ideas today is by the printed word. While this medium serves its purpose well, the overall effectiveness can be greatly increased and personalized by adding the supplement of sound with its infinite assortment of inflections. Here, then, is our objective: to raise substantially the rate at which information is transferred to the reader-listener. And now, I am extremely pleased to present the first guest speaker, Charles Simmons, Transistor Application Specialist of Philco's Lansdale Semiconductor Division. The subject of Mr. Simmons' talk on this and the 3 records to follow is high-frequency transistors, their characteristics and application.
In this first talk, we will discuss modern high-frequency transistors, and we are going to define 2 figures of merit for them. In Section 2, we will concentrate on the communications field, and we will consider optimum circuit design. In the third section, we will devote ourselves to high-speed switching and to a very important theory relating to this application. In the last section, we will discuss video amplifiers, and then talk a little bit about what is going to become available in the next few years. The first figure of merit I would like to define pertains to communication circuits, and the second to switching and video amplifier circuits. Let us suppose we have an optimally designed tuned transistor amplifier, in which all of the internal feedback of the transistor is completely neutralized. If one plots the power gain versus the center frequency of this amplifier, one finds that the gain behaves as shown in Figure 1. This is not a curve of the bandpass characteristic of the amplifier. It is a curve of the power gain at the center frequency versus the frequency at which the amplifier is operating. Now, for most modern transistors, the gain falls off at 6 dB per octave in the high-frequency region. This means that the power gain falls by 4 to 1 for each doubling of the center frequency. The gain of a tuned transistor amplifier turns out to be almost independent of the bandwidth. This is a very important feature of a transistor, which makes it considerably different from a vacuum tube. Actually, the gain is somewhat lower for very narrow band amplifiers and for very wide band amplifiers. Figure 2 shows how the gain actually varies with the bandwidth for a single stage of a 60 megacycle radar IF amplifier using the Philco 2N502. Since the gain is almost independent of the bandwidth, Figure 1 may be considered to be a universal curve. And the entire high-frequency portion of Figure 1 may be defined by defining the frequency at which the power gain is equal to 1. This is the highest frequency at which the transistor will oscillate, since a device must have a power gain greater than 1 in order to sustain oscillation. This frequency is called Fmax. Now, since all modern transistors behave approximately as shown in Figure 1, a knowledge of the Fmax of the device implies a knowledge of the power gain available at all frequencies in the high-frequency region. The last few years have seen a significant increase of the Fmax of the transistors available to the circuit designer. 2 or 3 years ago, the best units had Fmax of about 500 megacycles. Today, transistors are available with Fmaxes over 1,000 megacycles, and prototype units have been constructed with Fmax in the 3,000 to 5,000 megacycle range. Figure 3 shows the available gain versus frequency curve for a modern high-frequency transistor made by Philco for television tuner usage. Now, going to the subject of mixers and converters, analysis of these circuits show that they have approximately 3 dB less gain than the same transistor operating as an amplifier. Therefore, mixer and converter operation follows the dotted curve of Figure 1. Thus, Fmax is a convenient figure of merit for all communication circuits. The second figure of merit, which we shall discuss, is of prime importance in switching and video amplifier circuits. If one plots the magnitude of the common emitter current gain of a transistor as a function of frequency one obtains the characteristics shown in Figure 4. For all modern transistors, the current gain falls off in the high-frequency region at approximately 6 dB per octave. This means that the current gain falls by a factor of 2 to 1 each time the frequency is doubled. Now, the frequency at which the current gain is equal to 1 is called the F sub t, or the gain bandwidth product. It turns out that this frequency, F sub t, is directly proportional to the switching speed of the device in many circuits, and is also directly proportional to the gain bandwidth product that can be achieved in an optimally designed video amplifier. Thus, for untuned amplifiers and for switches, Ft is a primary figure of merit. Here again, the capability of available transistors has been increasing rapidly. 2 years ago, an Ft of 200 megacycles was exceedingly good. Today, many units are available with FTs of 400 to 500 megacycles, and prototype units have been built by Philco and others with FTs as high as 1,000 megacycles. Note that Fmax and Ft are unrelated. The first applies to tuned circuits and the second to untuned circuits. Transistors can be optimized for one or the other. In general, good high-frequency switching transistors are not good amplifiers, and vice versa. The alpha and beta cutoff frequencies have been used in the past to describe a transistor. Alpha cutoff is a number somewhat like Ft, but it can be demonstrated that for almost all applications, Ft is more fundamental. The beta cutoff frequency is a derived parameter, which is given by equation 1, and it is not fundamental.